So I went over the exam last time, but I did not record it. So if you got the exam back and have a question, you could talk to me after class. The lecture video got put up, I think, the night before last. So it's available. I was looking at the book, and I'm going to come back to some of the things in it, but I think that something I did about a year ago is better. But it's from another book. So I'm going to cover this section in the other book, and I will give you the notes on it, but I don't have them available for you yet. So you'll have to follow along, but I will post these notes. And then I'm going to come back to Chapter 5. We were ready to start Section 3 of Chapter 5 on regular expressions. The book I'm going to use, which I had a pre-release version of this book in PDF. If I can remember where it is. I think it's here. So this particular book is called Data Technologies by Paul Morell. And on Chapter 9 is dealing with R programming. And I think it's Section 9 of Chapter 9 is dealing with text processing. And I think that this gives a clearer explanation. And in particular, we'll look at the code. Because it's one of the things this example does is systematically go through an interesting example. So I'm going to kind of go back and forth between this and the code. Currently, the code is under Stat 623. So if I go into courses, and again, I'll pull this code out and post it. So into 623, Chapter 9, Section 9. I think this is right. Yeah. Okay. So just to give you a little context, this first example case study is going to be the longest place name. Now this is the actual name of a place in New Zealand. So what is this name? What happened? Oh. That's the name. I believe it has 85 letters. And it means the hilltop where the Tamaka, with big knees, conqueror of mountains, eater of land, traveler over land and sea, played his kawawa, flute, means flute, to his beloved. It's a long name. This is the native population of New Zealand, the Maori. So we want to do some text processing on that. Now, relatively speaking, this example is easier than some. So this is in a data set. So I'm going to, I need to make sure that I'm in this directory or it will not find the data set. So I'm going to I'm going to scan. I have file path, and then notice I have dot dot slash dot dot slash data sets. Do you know what that means? What's dot dot slash dot dot slash? File dot path is the Unix file path. If I say dot, that means your current directory. If I say dot dot, that means your parent directory. So if I say dot dot slash dot dot slash, that means the parent of the parent, the grandparent directory. So if you actually look, I don't have this particular. If you actually look at the directory structure, is this it? Oh no, I'm in my directory structure. I got to go here. I'm still in mine. What's that? Oh, here's chapter 9, yeah. And in 9.9. My point is, I'm here. I have to go back to here, back to here. So in other words, here are the actual data sets. And here's the place name right here. Of course, I could also show you what, I could also find it from here. Okay. So what I'm going to do is I'm going to scan in the text. There's a scan function which will scan that line. And the file path is a R command that says, well, what is the file path? And so I gave it back to the directory. And then it looks within that directory. It's a data set called directories, but it's a couple levels up. There's a file called place name.txt. And the character says that these are going to be character values that I scan in. So let's do that. And then let's write it out, and that's the name. Because last time we talked about the fact that we could string wrap. So if we wanted to wrap the strings, we could wrap that output such as wraps at after 30 characters or whatever. You may remember that. Now, how many character in char? This is kind of a review. We've done this before. There are 85 characters. And then gsub. Now, gsub is a very, very useful. You have a string, and then you have, in the second argument, you have the replacement. And in the third argument is what you're going to, it's the string you're going to use to replace. So anytime you find an ng in place name, you're going to replace it by an underscore. Is that clear? So the first argument is the replacement. The second argument is the replacement. And the target, what you're searching for, is the first, which is ng. Now the reason this is because in the Maori language, the ng is actually represented by a single character. Now, since we're not using the native script, we will simply replace it with an underscore. And likewise, the WH is represented by a single character. So if I go in, I'm simply going to name it replace ngs. And if I do that, this says every time I find an ng, replace it by underscores. So let's take a look at it. So you can see there are a few underscores here, right? There are a few underscores. Now this is actually shorter because 2 characters got replaced by 1. So this is actually shorter than the one above it. Now I'm going to replace the WHs by an underscore. So if I do that and then print it, now I replaced the one I had already replaced. So I have underscores whenever there's a ng or a WH. Now later on, we're going to see that we can actually combine those into one step. Okay. Now how many characters do we now have? We now have 80. Now each 2 letters went down to 1, right? So there were 5 of those. Now, what I'm going to do now is I'm going to use a function called G-regular expression. Now this is where a diagram kind of helps. There are certain commands that are useful. Suppose you have a vector string. What do I mean by that? Suppose I have a vector with 3 elements. And the first element is old pond. And the next element is a frog jumps. And then the third element is the sound of water. So I have a vector of length 3. And each element are those 3. In other words, old pond is the first element. It's a string. The second element is a frog jumps. Okay, so I have a vector of strings. Does that make sense? If I would say length of vector, it would say 3. It's a length of character strings. I mean, you know, these are character strings, each element. Now, if I say grep of D, it will find which strings the D occurs in. So that says old pond. It says there's a 1. Why? Because in the first element, we found D. But we don't have a 2 because there is no D in that second string. But there's actually 2 D's in the first one, but it's just asking, did you find it? Did you find one? That's all it's asking. And the last character string, it found a D. So there's a vector return. Grep returns a vector, and it simply says for each element, did I find it or not? Now, I have D, but it could be any string I'm searching for. It doesn't have to be 1 character long. It could be, it could be 3 letters or whatever. And it is case sensitive. So grep simply tells you which elements of the list you found a particular search string in. So if I got this big file and I'm looking for a search string and I want to see which lines it is in, if I had a file that ends in new lines, I could actually then take that file and bring it into a character vector where each line is now a string, and I could search. There are various ways you could do it. But that's what grep does. Now there's regular expression and G-regular expression. And there's a big difference. Regular expression, R-A-G-E-X-P-R, of D, it says what? It finds the first instance, and it tells you the location. So old pond, the first D is the third element, the third position, right? So there's a 3. I'll tell you about the right-hand side in a moment. And then, what about it? The next one? Well, there are no D's, right? So in that case, since it didn't find any D's, it returns a -1. That means it didn't find a D. And then the third string, notice that in position 9, the last letter of sound there's a D. So 3 minus 1, it said. Again, we know that it's only in 1 and 3, but this also tells the position. Not just whether it's there or not, but it tells you the position. Now, the second vector beside it is actually an attribute, and it tells you the length of the string you find. In this case, D is of length 1, so it's 1 and 1, and the -1 corresponds to not finding it. So that's the second vector is an attribute that gives the length. In this case, they're just 1 because I'm only searching for a single character. Now, there are various reasons why you may want to find all occurrences of D, or whatever string you're looking for, not just the first occurrence, but every occurrence. And now it's not enough to just say, in other words, in the case of the first one, the 3 is not enough, right? Because there are 2 Ds. So when I use regular expression, I get the 3, but that's only the first one. What you get returned from G regular expression is a list. So this is representing a list. This is one element of the list, this is the second element of the list, and the third element of the list. But each element could be a vector now, and each vector within that has an attribute. It tells you the length. So what do I get when I do old pawn? That maps to the first element of the list, which is a 3 and an 8. In other words, it finds the first D in position 3, and then in position 8, it finds the second D. So 3 and 8, they're both of length 1. A frog jumps is again -1 and -1, but that's an element of a list. And then this sound of water, it finds it in position 9, and it's of length 1. So this is the representation of a list as opposed to a vector that looks like this. But notice there's more information here. So each element, there's one element for every string. In this case, we have 3 strings in our vector of strings. Does this make sense? Now there's another function that we're going to find handy. Maybe we've talked about it before, but I think this is a nicer representation. And that's string split, str split of D. This has split on D. And this also creates a list. Because if you have multiple Ds, you will get multiple splits. So old pawn. So you get the first D, you get OL. And then I have a split, and then it looks at the rest of that and it finds the second D. And so it gives you a space PON. So it's split up old pawn into 2 substrings, where D was the divider, and D is not part of it. But I had 2 Ds here. A frog jumps comes through just as is, because there's no D. And then the sound of water, well, it gets the sound without the D, and then a blank of water. Okay? So these are 3 very useful string manipulation functions. So let's go back someplace here. And so here I'm going to use G regular expression. I'm going to look for NGs. I want to find out where NG is in place name. But notice I have double brackets 1. Why? Because G regular expression returns a list. And so I've got to drill down to the actual data. So if I run it and then do it, you'll see that NG matches occurred. Remember, there are 85 characters. It occurred in the 15th, the 20th, and the 54th. The NGs appear in the 15th, 20th, and 54th. And notice they're of length 2. It's an NG. So that tells you the starting positions, 15, 20, and 54, of length 2. And then I can do the same thing. Notice the WHs start in 8 and 70 of length 2. So what is the length? If that was called NG matches and WH matches, what are the lengths of these? Remember, that second thing is just the attributes. The lengths are 3 and 2. That's the length of these vectors, and it's really talking about, this is an attribute down here, so it's talking about this, the length of this vector, and the length of this vector, the 8 and the 70. Now, if I take the number of characters of place name minus the length of NG plus, look where the parentheses are, so I'm adding these two together and subtracting it from this. And I should get 80, right? So in other words, it's 85 minus 3 minus 2. It's another way of doing it. But this just illustrates the G regular expression, which gives a bit more information. It tells you actually where they are. Now, apparently, in New Zealand, school kids have to play with this word and try to count the characters. Suppose you had to find out how many of each letter appears. Well, it's not hard in R. You might find it hard to do. Well, of course, you could do it. You make a little tabular table, right? You do 1, 2, 3, 4, 5. You could go through and. But of course, you have to first of all identify the unique letters. You can't assume. I mean, how many letters are there in that word? I don't know. Well, let's do a string split, place name, and if I do a null, do you remember what null does? It splits it into individual letters. But string split returns a list, and so I'm going to drill down. Again, I use the double brackets. So if I do this and look at the names, there are all the names. Notice there's a capital T. So I'm going to now change everything to lowercase, so I'm going to get rid of that capital T. So I'll see 2 lower simply says I'm changing everything to lowercase because I don't want a small t and a big T to be different. So did I do that yet? I didn't. So let's do that. And now if we look at it, everything is small. And now we have a table of these here we'll do a table of lower name letters. And let's look at that. That was simple. That tells us how many times each letter occurred. Okay. And now if I look at name letters again, now that's before I did the, suppose you want to now put that back together as a single list. Well, we can do paste, name letters, collapse equals nothing between. And what that will do is recreate the sequence, the string. Okay, so that was a little fun exercise. And if you know R, you can do this very easily. If you try to do these things by hand, not so easy. Now, we're going to talk about regular expressions here. And so, remember when I said I went through all this rigmarole and to find the NGs and the WHs? So what we're going to do here is we're going to have an expression. In this case, it's an NG vertical bar WH. And you can read that to mean NG or WH. And if it finds either one of those, it's going to replace it by an underscore. So this is much easier than what we did before. We're still using G sub. And that just did it. Now, the vertical bar is what we call a meta character, and the letters get matched one by one, the WHs. But the vertical bar is what is called a meta character. So we're going to have these strings that will have literals, which match one to one, plus meta characters, which mean something more. And we're going to have some other operators too. And what we're going to be learning are what are called regular expressions. Now, there are really three types of regular expressions. There are basic regular expressions, and basically the basic ones have fewer meta characters. And extended regular expressions, which have more meta characters, allow you to do more things. And then there's the Perl version of this. This is for Perl compatibility. Now, there's not too much difference between the extended regular expressions and the Perl regular expressions, but there are some. R supports both. Now the next example that I'm going to do will use the extended version of regular expressions. So suppose you're a statistician. You go out on a project and someone, let's see, if I have this. If I can remember. Oh. So someone gives you that as their data. Now you may think that this is unrealistic, but I'm working in a project in linguistics where the data was actually much worse than this. That's the data. And you want to do, notice the RB. This has to do with wheat, and there are two diseases. I think it's brown rust and is it red rust? And then the number after it's the actual data. So this is a type of disease, and the number after it's the data. And then all the other stuff are just like notes and stuff that aren't the real data. They may be notes the researcher wrote down in the field. Let's see, the book. Okay, let me just read. Okay. So it says this is in 2007. This is a French study. It says due to unusual conditions, the two other diseases, I'll just call it brown rust and yellow rust, were also observed to be prevalent. And so so at any rate, this is the file. R has a different read commands, read.table, and that sort of assumes that it's in rectangular format, but not necessarily in what's called a fixed width format. A fixed width means you're in a specific regions as you go down. So fixed width format, which is FWF, means that it's the way we used to read things in Fortran. It's like you have to be in these columns and in this column. You exactly specify the columns your data's in. And you may record, I mean, if you're a neat type person, you may do that. But if you run them together, you say, okay, this is in 1 to 5, and the next one is in 6 to 10. There's no separator, right? So you have no separator. But that's okay if you know it's 1 to 5 and 6 to 10. So that's, that's the fixed width format. Now that's the data. And let me show you what you want to end up with. What you want to end up with is a data frame that looks like that. We have two columns. We have, did I say brown and yellow? What did I say?
Brown rust.
The first column is the brown. And notice that for the different plants, if it only had, like plant 1 had brown rust but no yellow rust. Plant 2 had brown but no yellow and so forth. But plant 11 had yellow but no brown. They could have both, which 18 does. Now, there's not a whole lot of data there, so if you were trying to analyze this, you might be in trouble with only 2 observations for the yellow rust. But at any rate, that's beside the point. The question is how do you go from that first format to this? Now, you may think, it turns out a lot of times that you spend more time manipulating data than you actually do analyzing data. And if you look at this example, you can see why. So someone comes in and says, here's my data. And a lot of people, the most common thing is to give you a spreadsheet where your data is here and you've got all sort of stuff around it. And of course, what you have to pull out is that and then reshape it. Because what a lot of people do is they'll take this and then they get sums and row sums and column sums and they do manipulations in Excel. That's not the way we do it. So we have to pull out the data and then reshape it. That's very common. The most common format you'll get data in is Excel. That's because that's what most people know how to use. And so they try to do statistics in Excel. Well, you can do a t-test. And in fact, you can do more than that. I wouldn't recommend it for a couple of reasons, one of which is the numerical accuracy. But there are it's just not an environment you can sort of grow with. In other words, you can do some basic things, and there's some add-on packages that do a little bit more than basic, but you're going to be very limited in what you can do. So you first of all want to get it out of Excel into a format that's going to be usable, and you're not going to be limited. But certainly the format that you started with here is nowhere near what you need it in. So going back to our data now, again, did I read it already? No. So we're going to read this in. And here's what it looks like. Now, that's actually observation 1, 2, 3, 4. Second line is 5, 6, 7, 8. So when I showed it to you here, this was the stretched out version. That's the same thing as this, right? So this is the way we read it in. So this is what we now have. That's what we have. So how do we use regular expressions to go from that to a data frame that has the two columns? Each row corresponds to a wheat plant. Oh, I don't know how they did it, but something like that. And then you're measuring how much of each of those two rust diseases. So, first of all, we're going to grep. Now notice we're searching for RBs. We're searching for it's always RB. First of all, I'm going to search for the RBs. Forget the other variable, the other type of rust. Forget it. I'm going to look for RBs first. RB space, and then I have a number, but then it may not be a single digit. It could be more than one digit, right? So, this looks strange. I've got RB space. Those are literals, exact matches. Then I've got brackets. And it says, followed by any digit between 0 to 9. But there could be more than one, and that's what the plus means. The plus means one or more. So that means RB followed by a space followed by one or more digits. It's going to match that. We're going to see, so what are we going to do? First of all, we're going to say, okay, let's do that. And that tells you the lines of the data. That's line 1, 2, 3, 5, 6, 9, 14, and 18 have an RB followed by a space followed by one or more digits. So we found the line numbers. That's a start. It's only a start. And now I'm going to subset it. So that's actually that subset of this bigger. Those are the ones that actually have the data. Now, let me just do this next one and then I'll talk about it. Now it looks like we're getting someplace, right? We have just the RB space 2, RB space 2, RB space 3, and so forth. We've kind of gotten the crux to what we need. Now, this //1 is called a back reference. So here Now this looks weird. I have a caret dot star. That's actually an asterisk. And what this means is, the dot means matching any single number character. So the caret means, in this, carets have different meanings depending on where they are, but in this case it means the very first position, the very first start. And then it says one or more of anything. The asterisk means zero. The plus means one or more. The asterisk means zero or more. So this says from the start position, one or more of anything. And then I have parentheses. That starts a matching sub-expression. That starts a pattern. And that pattern is, basically I have an RB someplace, and I may have junk up to there, and I want to get rid of it. So on the front end, I want to get rid of whatever's before the RB, I want to get rid of. So what I'm matching is all that junk. Caret dot asterisk does that. Caret says start in the first position and find one or more characters until I get to the point that I'm going to match the RB. RB space 0 to 9 plus in parentheses. Now I have a dot asterisk dollar sign. The dollar sign anchors the last character of the string, just like the caret anchors the first. And this says now 0 or more characters until the end. So what it does is I'm finding the relevant part, and I also have matched the two parts that aren't relevant. Anything before the RB and after the number, anything is going to, I'm not going to want it. And that's where the second argument now says //1. That's a back reference. That 1 is referring to what's in the parentheses. That's what we're actually matching from wheat, and we're doing wheat RB lines. Wheat RB lines subsets the group we want. Remember we found RB lines? So that subsets the group we want, and then it's going to match that inner part and throw away the rest because it won't match. So that's what this //. Now, if you read this in our book, you will be scratching your head on the //1s and the //2s. But I'm also going to illustrate //2s, what that means. So what it's doing is, this is actually what the //1 refers to the parentheses, whatever is in it. If I had a //2, if I had parentheses and another set of parentheses inside the first set of parentheses, it would refer to those inner parentheses. So I can do even more sophisticated searches, have parentheses within parentheses that I replace on. So again, I'm going to do a replacement. And so this is what we end up with. So in other words, look at number 1. It has LEMA, comma, space. All that's gone. And what made it go was the caret dot asterisk. And notice a lot of them have a percent sign at the end. That's gone. That was gone because of the dot asterisk dollar sign. The percent is the last. It's the dollar. It's where the dollar sign is. So anything from the RB space number, even if that number has a couple digits, anything beyond that is gone. Okay. So notice the sixth observation. You see it has little notes there. I suppose those notes are in French. Everyone know French? So at any rate, so we're making some progress here. Also maybe taking a long time. No, we have some time. Okay. So now we're getting someplace. Now notice this caret. That means when I put a caret inside these square brackets, it means negation. So 0 to 9 means any digit. Caret 0 to 9 means anything that's not a digit. So what I'm going to do now is I'm going to replace anything that's not a digit by a blank. I have double quotes with nothing between it. So it's not even a blank. It's just, it replaces it by nothing. So what happens? What do you think is going to happen if I do this to RB only? It just got it. Now we only have the data. We know all these are RBs. And ultimately we need RB at the top and then the data. Okay. Now I could also have done this. It's also true that I could have done this with substring. Substring RB only, comma 4. That means now usually substring has two arguments. It has a start and an end. But if you only have one argument, then it means start here but go to the end. So I could also have done it this way, and I get exactly the same thing. So I could have two different ways to do exactly the same thing. Because the number always starts in the fourth position, right? You have RB space and then the number. So the number always starts in the fourth position. And even if you have more than one number, it's okay. Because if I give one argument, it says start in 4 and go to the end of the string. Okay. Now this is sort of the same thing, except here, here I'm going to, well, let me run this. Now that's the same too, and this is a more complex argument. This is using the //2. Now the expression that I gave, the expression right here, this part looks almost the same as what we had before, except for the fact that I have another set of parentheses around the brackets 0 to 9 plus. Notice that's in a second set of parentheses. Do you see that? So when I say //2, that's a back reference to the inner parentheses. And so what it's going to do is going to simply match on that. And that inner parentheses is simply the data. Okay, so you're going to think, who came up with this? But it's very powerful. It's just kind of cryptic. But it's extremely powerful for searching. And if you're writing a parser, if you have a computer language and you're writing a parser, you could really use regular expressions. I'm not saying that's what you would use, but you could to parse the code. Okay. So, where am I? Okay, let's go back. And I'm going to create the length of wheat. I'm going to create an NA. So I'm creating a vector of NAs for the length of wheat. But then what I want to do is replace the NAs with the observations that actually have data. Well, we know which ones. Remember, we found out which of those have data. And we in fact called that RB lines. RB lines, if you go up and look at it, remember that was that grep. That told us where the data was. So I'm going to replace, I'm going to take RB of RB lines, and I'm going to, let's see, where am I? Yeah. I'm going to replace this G sub of this //2. Okay, so let's take a look here and see what we get. Let's look at RB now. So the first operation gave you it gave you all NAs means not available. It's not a number. There's no data there. That's what it means. That's the typical thing R uses. So that first expression right here, where am I? Right here, line 47, that gave me a vector of just NAs. But then it said, remember when I said there are certain positions where the data is? And so we found that was what we called RB lines. That said, we have data in the first, the second, the third, the fourth, the fifth, the sixth, and so on, but not where the NAs are. And so I basically have a replacement function here. I have RB of RB lines are going to get this whole expression we found, which actually gives the data, and we're going to coerce it to numeric, and that gives us the vector. So we got one of the two vectors now. Now we have to do the same thing for the other variety of wheat, and we could do it exactly the same, the disease, the rust. We could do it exactly the same, but we won't. I mean, obviously what we just did, we could do twice. And then we could make them into a data frame. But let's see if there's something that's a little bit different. So let's do a regular expression. And I'm looking for Rj space and then one or more digits. And I want to find out where this will tell me where it occurs in wheat. So this says that it only occurs in I think that's the 11th and 18th position. And then it says it's of character length 5 and 5. That's because both of those are Rj space 2 digits, I think. Yeah. Okay. So that was using regular expressions. And so that gives the position. The minus ones mean you didn't find it in those. Remember we talked about that before. You didn't find it in those strings. And so you get minus ones. And now we're going to do a substring. We're going to do a substring on wheat using RJ data, but we have to take into account the attribute which gives the length. And this is something that substring supports. The attribute will give the length on match.length. It takes RJ data with match.length, and it will actually give the length, and then it knows how to substring it. So if I now do that using substring, and let's take a look at RJ data. So that's our data at this point. This is a very different way than we did it before. The two quotes mean there is no data. And notice in the 11th and the 18th positions it has the data. For just those two. That's the only place we have data for the other rest. And now I have to just pick out the data. So I'm going to do a substring starting in the 4th position till the end. And I'm going to coerce it to numeric. And so if I don't have it, but if you look at RJ, it now looks like that with these 2 digits in it. And then finally, I'll make a data frame with RB and RJ. And there it is. Simple. Well, it's not simple, but once you start thinking in terms of regular expressions, it's not as hard as you might think it is. So how would you have done it? You would have typed the data in again, right? Which would be okay if you only had that much data. It wouldn't have been okay if you would have had thousands of records. Besides the fact it would take a long time, you would make mistakes. So the idea is that this wouldn't have mattered how much data there is. There could have been hundreds and hundreds of these. You could have many, many wheat plants where they measured this. Wouldn't have mattered. The process would have been identical. Nothing would have changed if you had 1,000 wheat plants that you measured rust on for these two species. Wouldn't have mattered. So that's the whole idea. If you have a little data set, yeah, I can do it right here. Not what you're going to want to do in general. Of course, this isn't necessarily how I tell the experimenter to measure the data. But a lot of times, they don't come until they collect the data and they say, here's my data. And then you've got to figure out how to get it into a form that's analyzable. Okay? So I'll pull this stuff out and post it. Are there any questions? This explanation is, even though that's a fairly complex example, the explanation in this book is far clearer than the explanation in our book. And our book doesn't really give a big example like this that shows, hey, this is kind of useful. Okay, I was going to go back. I think I have a little bit of time. Yeah. So I want to go back and look at our text because it has some additional things in it. So we'll go back and take a look at a few things. So at any rate, this book is called, I don't actually have the title. I mean, I don't have the cover. This is sort of a pre-publication book. This is called Introduction to Data Technologies. And just to show you some of the things in this book, because this is a book we used in 623. But one of the things, for example, here, this is on SQL databases. Well, this and this. And XML is the language of the web. Well, it's really HTML, but a more sophisticated version of it is called XML, which HTML stands for Hypertext Markup Language. And it's the standard thing people use. And the current version is HTML5. And then you combine this with style sheets, what are called CSS style sheets. And you can get very sophisticated formatting with this and other things. And then if you go into XML, which stands for Extensible Markup Language, it's a much richer version than the HTML. And a lot of times data and information is stored in XML format. So the question is, if you have your data stored in XML format, how do you extract it? Again, you get into the problem of, well, okay, how do you extract it? And XML format is one of the common ways to store information. Now, there's another way that's commonly used, what's called JSON. The J meaning JavaScript. It's a JavaScript, originally JavaScript, but now it's an open standard. And then SQL databases. But there's a new book coming out called Web Technologies by Duncan Temple Lang and Deborah Nolan. He's at UC Davis, and she's at UC Berkeley, but he's her student. And they wrote this book called Web Technologies, which is coming out in the spring of 2014, which is really, really good. So I think when 623 is called again, it'll be a combination of this book and that book, because it does some very powerful stuff for, like I said, if you want a job at NSA, you have to know this stuff, because you go out and scrape the web. So at any rate, and then this chapter 9, it's basically the R programming language, and it gets into things. It gets into things that go well beyond what we have done in terms of how do you reshape data and things of that sort. If you've had SAS, you have all these things like concatenate and merge and so forth, and all of these things can also be done in R. Okay. So that book is a pretty good book, and actually it's fairly easy to read. Okay. Let's go back to our book. So go back to courses and go back to 523. And we're in chapter 5, section 3, which is regular expressions. Well, before I do that, I want to reset the directory. Can't remember if I need to do that or not, but sometimes you do. Well, if you look at the book, basically what the book says is the / less than will tell you the position of the first letter of every word. So this should give 1, 4, and so forth. But it doesn't. If you actually look at his book, you will see that it's giving the first letter, the position of the first letter of each word. Well, let's see what happens when we do it. It actually gives 1, 2, 4, 5, 6, 7, 8, and there's no 9. So what it's doing is it's giving every position that there is a letter, but it's not giving the spaces. So I tried to look this up, but it appears that they've redefined the / less than. Remember, the double slash, the first slash is an escape. So it's really / less than. And again, they apparently, by they I mean the R team, someone in R, someone in the core R has redefined what / less than means. So instead of just giving you the first letter of each word, it's giving you the positions of all letters. But if it's a space, there's no position. So that's why you have 1, 2, there's no 3, because the 3 is a space. So from this, you could find the first letter. Now, on the other hand, when I do this, the greater than finds the end of the characters. So it actually tells you where the spaces are. So the third position is a space. And then the ninth position? 2, let's see, 5, 6, yeah. The 9th position is a space. And the 16th position is the end. And so that tells you where the spaces are. And notice that it gives, even though the quotes stop at 15, it's giving you one more than that. Now both, the B is going to give you everything here. It's the combination of those two. And this is once upon a time. And then when I do this, this is the same thing, just on a different string. Now the caret is 1. That's because the caret gives the first position. We knew that from before, right? And what do you think the $ gives? Okay. It's giving the last position. But here, it's actually giving where the quote is, I think. So, okay.
What's the B?
B means both. It means both the greater than and less than. It's the union of those two.
Why would you want both at the same time?
Well, under the old definition, you would. Under this definition, it just gives you everything. But under the old definition, it would give you the start and the stop of each. It would give you a start and stop of each letter. But under the new definition, I'm assuming this isn't a bug, which is possible. But it's hard to imagine it's a bug. Okay. Now, suppose you were looking for R. You want R. So we're doing a search where we have or, and then we have brackets, and we have caret or. What do you think caret or means? I told you. Within brackets, it means the negation. It means not or. When you have a caret by itself, it means the first position, but a caret within square brackets means the negation of whatever follows. So this says, I want to search for something that's an or followed by a not or. Okay? So I want an or followed by a not or. You can see in genomics how this might be useful, where you're searching for certain genomic sequences. In fact, this is what this is used for by bioinformaticists. So when I'm doing a regular expression, and this says in the fifth position, I have a string A, S, F, F, R. In the fifth position, I found an or followed by a not or. That works. But what about here? Or is at the end. So it's not an or followed by a not or, so it gets a -1. So how can we fix it? Well, there's something called look ahead. And the book discusses, there's all a look ahead, a look behind. So this is sort of looking ahead. And it's sort of like I'm looking ahead, and I can detect, in this case, the $ explanation point is a negative look ahead, meaning there's no R. And so if I do this, it says it's in the fifth position. Wait a minute, that's okay. That's the one we did before. It's the next one where I don't have the last digit. So that's in the fifth position. So is this. This has ASFFR, so R is last. There's nothing after it. But I did a look ahead, and that's what I did with the question mark explanation. And that's basically that explanation. We often do the explanation point as a negation. And so that's a negation. I'm looking ahead, and it's a negation of having an R. And so that actually finds the R in the last position. So that, the first way we did it, right here, the R brackets not R is not as good as the second way we did it, because the first one will not find an R at the end, whereas the second way does. Now, as I said, this question mark explanation point, there are various versions of those that look ahead, look behind, and so, there are various versions of that available. Okay. Oh yeah, is it time? I don't want to. Oh, okay. Go a little bit longer. So here's a regular expression: A to Z, capital letters, //1. That's that back reference into what's in parentheses. And if I run this, it's going to find an AB, and it's going to find an AB. Let's see. No, it's finding a BB starting in 2, and let's see, and then a ZZ starting at position 5. So that's the example we gave is a lot better than this previously gave. But there are some funny things. So, for example, if I look at AB, a regular expression of AB 2, 4, that means at least 2, but at most 4 occurrences of AB. Okay, so in this case, I'm only finding 1, which is just the AB. Is that what? But in Perl, this says Perl equals true, which is using Perl. It's actually giving the same thing. So I'm not. Okay, never mind. Okay, that's not a very good example. I was thinking it was a better example. Maybe it was in the other book someplace. That's not a very good example. If you look in the book, instead of having a beginning at like 2, and that means at least 2 and at most 4, you can actually just say, I want 3 occurrences, and you don't have the comma. So that, again, you can look for certain string patterns. What you're doing is looking for string patterns, and that's why, as I said, in genomics, you're often searching sequences, trying to find certain patterns. Okay. This example we've actually done before. This is foo, vertical bar, foo bar, and the string is my foo bar. And so it says find one or the other. Well, actually, both of those occur in foo bar. And so, it says beginning in position 3, it finds it, and the length is 6. So what it's finding here is the longest one, which is foo bar, which is length 6. And if you do Pearl, I think it gives a slightly different answer. Yeah, it says 3 of length 3, which is finding the foo, not the foo. It finds the first one. So it finds foo, not foo bar. So there are some subtle distinctions between the extended set and the Pearl, and that's always illustrated. See, a lot of people only use Perl as a separate language. And I think that there was a book I maybe mentioned to you before called Bioinformatics Using Perl, which does string sequences, but it's only using Perl. So if you want to be compatible with Perl, then R lets you be compatible. If you've written your code in Perl or you know Perl, then you may want to use the compatibility of Perl to do it here. So, okay. So, okay. Here's a test string, and this is a GNA sequence. And then we're going to look for a G-regular expression in this test. If we notice that ACT, ACC, ACT, then we're doing a G-regular expression. And it says, yeah, we found one of length 9. Now, notice, remember, G-regular expression from that other book, it's a list. So notice the double bracket here. This says, okay, we have a list, and we found, starting in the first position of length 9, we matched. Now, they have rewritten in one of their bioinformatics packages G expression 2. If you were searching sequences, you may want to find all occurrences of that sequence, but suppose they overlap. Suppose you have a sequence, and then within it you have another sequence, and they overlap. It's the same sequence. The G-regular expression will not find that second sequence because it overlaps with the first. It will only find, non-overlapping. So they've written one called G-regular expression 2, which lets you find non-overlapping. Now notice, let's see, do I have overlapping ones here? Yeah. Oh yeah, here's the original string. I have ACT, ACC, ACT, ACC, ACT. So notice I have a second overlapping one starting here. So my first one starts here and ends here. My second one starts here and ends here. So they overlap. So let's see if we can find both of those. So if you do that, it says it finds it in the first and 7th position. It has one of them starts at 1, one of them starts at 7. Okay? So if you're doing genomic sequences and you were looking for strings, that's why they did this. You would need, if you were looking for certain strings, you want to know even the overlaps, where they occur. Okay, so that's okay. I think this is actually I'll stop here, but this is looking at month, day, and year. Suppose you have DD, Y, and you're searching for years, and you want to match on that. The reason you have //D // is you have to escape the slash. So at any rate, we'll start here next time. So we'll start looking at times, and we're going to do a few more we'll do a few more bioinformatics examples in the text. So if you look through the rest of this section and into the next couple, we'll do that, and it's probably just been one more lecture. To tell you where we're going chapter 6. If you're programming in C or Fortran, it's for you. That's actually external routines from another language that you can then write and then compile it into your R code. Now, if you really want speed, there's a package that lets you integrate C++, which will even go faster, typically. And there's also interfaces to Java. Then the next section, the next chapter, we will do, and that relates to creating an R package. So what we're going to do is look at the basics of creating an R package, and guess what I'm going to want you to do? Is take your S3, what you did for assignment 2, and make a package, an R package. So you'll be an author. Not that you're going to get it published up on the R website, but we'll learn how to write a package. And then the last part of the course, whatever we have time for, is data technologies, which is what that other book was called. So there are certain parts of it we'll do. Whatever we have time to finish there, we'll spend the rest of the semester on. So that's where we're heading. So there'll be an assignment on this chapter, and then there'll be an assignment, probably an assignment for writing a package, and that will be 5, I believe. How many assignments am I doing? What now?
2 more will be 5.
Yeah. At any rate, so there may not be an assignment on chapter 8. Again, that's going to be sort of whatever we have time to cover in that last chapter. Okay, that'll be it.